In this video, we're going to discuss polynomial functions. The general form of a polynomial function is written like this. We start with function notation, which is f of x is equal to. Now, because this polynomial function can, in theory, have infinite terms, we have to represent them in a slightly different way than we are used to seeing. So what we do is we represent all the coefficients with the letter a. But since all the coefficients are not exactly the same, we then give them a subscript. So in this case, a sub n, and then times x, your input variable, to the nth power, plus. Then we go to the next one, and we say again, it's a coefficient of a, and we call this a sub n minus 1, saying that basically they are, or at least potentially different. And then times x to the n minus 1 power, sorry, that is an n, plus a sub n minus 2 times x to the n minus 2. And what you do is keep going for as many terms as you possibly have. And so we write a dot, 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 meaning that there's potentially a lot of terms, and maybe just a few terms in here that we're not going to write. And then finally what you get to is a sub 1. You continue to decrease from n, your highest exponent, times x to the first, and then plus a sub 0, and we don't write x in this case because x to the 0 power is 1, and 1 times a sub 0 is just a sub 0. So just a couple quick notes here. First of all, these coefficients. These coefficients have one special property, and that is that the coefficients are real numbers. Okay, so no imaginary numbers with these coefficients. Another thing that differentiates between a polynomial function and a different type of function, it would be the exponent. So the exponent in this case, n minus 1, n minus 2, all the way down to 1, and then finally 0. These exponents, or powers, are non-negative integers. So you might want to make a note that this means, number 1, they're not negative, number 2, they're not fractions, and number 3, they're not decimals. They have to be 0 or above, and they have to be integers, meaning no decimals and no fractions. The degree of a polynomial, all right, this one's pretty simple to and quick to define. It is the largest power of x. Okay, so the largest power of x. So if you have a power of x that's, say, 4, and it's the largest, then the degree is 4. We'll practice that in a problem here in a minute. For each of these 4 problems, we need to determine the degree of each function, of each polynomial, but the big catch is we can't assume that they all are polynomials, so we must first determine if they are. What you're really looking for is the exponent. So the exponent here for the first term in number 1 is a 1. The second one is a 3, which means that both of them are non-negative integers, so this is a polynomial. And so we look for the largest. So the degree in this case is 3, since the largest power is 3. Okay, number 2, now you notice here I do have a power of 2. This one would be a power of 0, although we don't ever write that. But we have a power of 3/2, which is a fraction. And we already decided or determined that polynomials cannot have rational powers. So this is not a polynomial, which means that there's no degree. All right, going down to number 3. Number 3 actually is a polynomial. It's not written in general form because it hasn't been distributed or FOILed. So you could FOIL this all out, right? X minus 1 times x minus 1, FOIL that out, then multiply by x squared plus 1, and then multiply by 2. That's a bit of a process, but you can do that, and by doing that, you'll get the right answer. Or we can just think our way through this problem, which is what I tend to do. So since we have a squared here, it means we're going to write this twice and multiply it out. So what we'll have here, the largest power of x with this first x minus 1 quantity squared will be x squared. Okay, We have a 2 here, but that doesn't change our power, so I'm not gonna pay much attention to this coefficient of 2. And then we have x squared plus 1, which means I will be multiplying these two together. So I will end up getting x to the 4th. Now, does that mean x to the 4th is the first term in your polynomial? We're missing the coefficient, and there's a lot more to it. But what we get here is the power. All right, so if that made sense, if that kind of you were able to piece that together as I did it, great. If not, then multiply it out, please. So the degree here will be 4. All right, with the last one, what you notice here is that we have a square root. Well, the square root of x is really equal to x to the 1/2. So when you multiply these two, you get x to the 1/2 times x to the 1/2, which equals x to the 1/4. So again, just like in number 2, this is a rational exponent, so this is not a polynomial, which means it technically doesn't have a degree. There is a particular polynomial function that is worth mentioning, and that is called the power function. The power function is a function of degree n, is a monomial function written in the form f of x is equal to a times x to the nth power. So a is your coefficient, and then n is your exponent, and that is it. There's no other terms. It's one term, which is why we call it a monomial. Okay, so properties when this exponent n are even. It's symmetric with respect to the y-axis. The domain is negative infinity to infinity, so all real numbers. Notice I left the range blank for this because the range really depends on your value of a. So when a is greater than 0, the range will be 0 to infinity, including 0. When a is less than 0, the range is negative infinity to 0, including 0. And here's why. Remember, the a actually affects two different things with our polynomial, with our power function actually. Number one, it's going to determine whether it's been reflected across the x-axis. So when a is positive, it's going to be opening up. When a is negative, it's going to be opening down because it's been reflected across the x-axis. The second thing it's going to do is change any vertical stretching or compressing, which we talked about in previous lessons. So just to give you a quick glimpse, I'm going to do a polynomial function where n is pretty large. So we've seen what it looks like when it's when n is 2, meaning we have a quadratic. It is a polynomial, and it forms a parabola. However, what if we have n which is pretty large? Well, what will happen, and again, this is just a sketch, so I apologize for the rough drawing, but what will happen is that it's going to decrease rapidly, but then flatten out in the middle and then increase rapidly. And that is a really rough sketch, but you see the big difference. Now, the blue graph is not considered a parabola. Parabola is a name term that can be only used for quadratic, which means in this case n has to be equal to 2. All right, properties when n is odd. It's symmetric with respect to the origin, and the domain is all real numbers. The range is also all real numbers. So I'm going to give you a quick graph, and for this graph, a is going to be greater than 0, but basically, again, the larger the n value, the more it flattens out like this. So it's going to come down here, it's going to flatten out around the origin, and then come down there. So it looks like a cubic function, and a cubic function is an example, but as n gets larger, it's going to flatten out here in the middle, which is why I drew it like that. So again, this is just an example, and these are some of the properties that you should know. Next, we need to talk about real zeros. If f is a function and r is a real zero, then we can say f of r is equal to 0. Now, believe it or not, you probably haven't heard about real zeros, but you have heard about basically some equivalent statements. So we say that r is a real zero We can also, this is number one. Number two, an equivalent statement would be that R is an x-intercept. Number three, we could say R is a solution to f of x equals 0. And number four, we can say x minus r is a factor. These are all equivalent statements. So r is a real 0, r is an x-intercept, r is a solution to f of x equals 0, and x minus r is a factor. Here's what this really means. R is a solution to the polynomial. You get that solution by factoring. One of the ways you can get it is factoring, so you get x minus r, and then you'd set that equal to 0. Whenever you solve a polynomial, and by the way, we've done this before when we solved quadratics, so you've solved a polynomial before, you always set it equal to 0 to solve. And when you do that, you're really finding the x-intercept, okay? So again, these are all linked together. It's just that we're now giving it a new name, and we're calling it a real 0. For these two problems, we will be forming a polynomial whose real zeros and degree are given, meaning I'm giving you the solution. You have to find the problem, kind of like Jeopardy. We're going to work backwards. So we know that x is equal to -2. We know x is equal to +2, and x is equal to 3. We're going to keep an eye on this degree, make sure we get a degree of 3 for our final answer. Well, I want these all to be equal to 0. Again, I'm working backwards, and if you go back and look at the work we've done with quadratics, that's what I'm doing. I'm working backwards from the solution. So now I have x plus 2 is equal to 0. X minus 2 is equal to 0. And x minus 3 is equal to 0. What I have now are the three factors of the polynomial. So I've got x plus 2, x minus 2, and x minus 3 equal to 0. I then can multiply this all out. So I'm going to FOIL the first two, so it'll be x squared. Whoops. After I FOIL it all out, I will then get x squared minus 4. And then I still need to multiply by x minus 3, which will give me x to the third minus 3x squared minus 4x, and then finally plus 12, and this is equal to 0. Finally, we'll write it in function notation, so it's f of x is equal to x cubed minus 3x squared minus 4x plus 12, and that is my polynomial function. Going to the second to last problem, I have, again, the same situation, but look here, I have this thing called multiplicity of 2. I'll explain what that is in a second. First, I'm going to set the -1 equal to x. Here I go x is equal to 3, and then I say it again because it says it has a multiplicity of 2. If it had a multiplicity of 3, I'd write it 3 times. Multiplicity of 4, I'd write it 4 times. I'm then going to again get my factors. So x plus 1 is equal to 0, x minus 3 is equal to 0, and x minus 3 is equal to 0. I write these out. And then I multiply them out. So it'll be x squared minus 3x plus x minus 3 times x minus 3 is equal to 0. Simplify the two middle terms, so you have x squared minus 2x minus 3 times x minus 3. And so finally I need to multiply again. So x to the third minus 2x squared minus 3x and minus 3x squared plus 6x and plus 9 is equal to 0. All right, finally, I'm going to do a couple things at the same time. I've got a -2x squared. I've got a -3x squared. And I also have -3x and positive 6x. So my final answer will be x to the third. Negative 2 minus 3 is negative 5. X squared. I then have plus 3x plus 9. And instead of equal to 0, I'm going to write it as equal f of x, which we usually write first. And I could have done that as well. So there's my polynomial function. All right, good luck.
Why did you write that?
Write what?
Why did you do all of that? Why?
Because I felt like it. I just love math that much.
I'm a speaker.
You are.
Oh my god! I want to be a teacher. Speaker.
Everyone hears you now.
No!
Say hi, class.
Hi, class. Bye. See you tomorrow, maybe.